So let's go through the next subsection in the book, the Cauchy formula for a disk. So subsection 3 to 4. Now, this is probably, the thing, the theorem that makes, that is the most useful statement of this circle of ideas, right? It's really the reason why holomorphic functions are so nice. Now, we're only gonna right now do it in a disk, just because the geometry is simple, and and it is something that we can do, and it follows by by the Cauchy theorem, right? It's the Cauchy theorem proves this. It's basically this idea that we can compute the formula at one point and use Cauchy theorem is a lot of times used to prove kind of independence of paths kind of result. It really is. That an integral around one path is the same as the integral around another path. So what is the formula, right? If I'm saying about how wonderful it is, right? So suppose that I have just some open set. Sorry, I wanted the highlighter, but maybe I'll make it a little thinner than last time. So suppose that I have some open set, some holomorphic function on that open set, and I have a disk around P of radius R, and I want the closed disk to be in U, right? So I want the boundary to be in U as well, right? So that's why I'm putting the closure, right? Because we're going to be integrating around the boundary, so we need F to be, at least nice and, let's say, continuous, right? So that we can integrate it there, right? So that's why we're doing that. It's, you can do, slightly less stringent hypotheses, but this will do. This gets you almost everything, right? This gets you the important part of the idea, right? Now, so if you have that, we're only going to be interested inside what happens inside the disk. So if you have a point inside the disk, right? This has to be internal, not on the boundary. So Z is some point inside the disk. I have a formula for what F is, right? F is 1 over 2 pi I, and the integral around the boundary of the disk, counterclockwise, of course, of this of this formula over here, right? So now, it should be a little surprising why this works, right? It might seem a little bit out of the blue, but why is it surprising? It should be surprising because the values inside, all the values of F inside, right, which is a fairly large set, are given in terms of some integral, so some sort of weighted average in some way, of the values on the boundary. So once you know the values on the boundary, you know the values inside, right? Now that's a little weird, right? That means that once I know the values on a very small set, I know them on the boundary. I know them inside. This is not going to be true for just any kinds of functions, right? So there's something special about holomorphic functions, right? That we have, we just need to know them on this one-dimensional set, and we know them everywhere, right? That should be weird, right? And it is weird a little bit. It also says that there aren't that many, and these functions are very rigid, right? So maybe one thing before moving on, notice that in this, is sometimes called the Cauchy kernel, the 1 over zeta minus z over here, because kernel is something that you integrate against, right? So notice that this thing blows up as z goes towards the boundary, right? Because this zeta will go around the boundary, right? So it will attain every point on the boundary at some point on the integral, right? So as z gets closer and closer to the boundary, this thing blows up, right? So that might be, a good thing to notice because it's that comes up in some estimates sometimes. All right. So let's prove this, right? So let's fix some z, right? We're trying to do f of z equals something. Let's fix some z, right? And to make things just easy to write, so I don't have to write this thing for the boundary of our disk, our big disk, I'm going to call it gamma, right? And again, it's counterclockwise as usual, right? Now, let's let this delta s centered at z, right? So this big disk is centered at P. Now we have a small disk that's going to be centered at Z, and I'm going to make it so that the whole closed disk is inside this big disk, right? So we want the whole closed small disk inside the big disk, and it's going to be centered at Z, right? So S could be really, really, really small, I mean, compared to R. If Z is close to the boundary, let's say, of this big disk, right, then you need to maybe choose a small s, right? But there's always some s. And again, to make things simpler, I'm going to call the boundary of this little disk, I'm going to call it alpha. All right, so this is sort of the picture, right? Now we're going to talk a little bit more about what we're doing here, what all those lines mean. But you have the big disk, that's the big circle. Yeah, that's gamma, right? Going counterclockwise. You have alpha, which is this little circle that's going counterclockwise as well. It's centered around z, right? Now, what we're going to do is we are really interested how is the integral of f related if we integrate around gamma and if we integrate around alpha. Now, what we're going to do is we're going to, basically connect up these paths in let's say 2 straight lines, right? You could just go, look at the straight lines for the origin and z, right, and draw straight lines along there, right, so that you connect up alpha and gamma. And now you define 2 new paths, right? You defined C1, which is going to be a path that goes like this, then goes like this, then down here and up here, right? That's C1, and it goes around in the direction that I drew it in, right? And you define another, let's call it C2, and it doesn't really matter where you start, but let me start over here, and it goes like this. So that's C2. With that orientation that I drew it with, right? All right. Now, as chains, going around C1, so, going around here, and then going around C2, right? You will notice that I traveled along these straight line segments that I added. I traveled twice, once in one direction, once in the other direction. What does that mean? The integrals just cancel out, right? So the integral around C1 plus the integral around C2, well, if I do that, the integrals around these straight line segments cancel out, and it's really just the integrals around gamma and alpha. And I did travel around gamma in the positive direction, right? I did half of it on C1, right, and half of it on C2, right? And then around alpha, I went clockwise, right? So alpha is oriented counterclockwise, in the standard orientation. So if I want to go clockwise, I have to add a minus sign over here, right? That's the reason for that minus sign, right? All right, so now I have that. Now notice that the reason for doing this, it sort of looks complicated, but the reason for doing it is that if I look on the thing that's inside the integral, right, the integrand in our formula, it blows up when zeta would be equal to z, right? So when zeta is equal to z, right? Well, that's so if I'm thinking of this as a function of zeta, right? This is a holomorphic function of zeta, right? I have f is holomorphic, right? And 1 over zeta minus z. Z is fixed. Remember, z is a fixed point, right? So this is just some holomorphic function. Well, in U except at Z, right? So it's not holomorphic at this point, right? Because that's where I'm dividing by 0, right? So it's no good there. But elsewhere it's holomorphic on U, right? And U contains this entire thing, right? I mean, U is bigger, it contains something outside of here, right? So now if I look on let's see, let's say C1, right? So C1 is inside a domain that's star-like that does not include Z, right? And really, it's this. Let me try to. Color it in. It's this guy over here, for example, right? So C1 is completely in there, right? You don't have to necessarily use this exact one, right? But that's one of the possibilities, right? This function is holomorphic on that domain. It is a star-like domain, right? I could pick a z0 somewhere here, maybe, right? That's going to make it a star-like domain. There are other choices. You could use like a plane with a slit. There's all sorts of choices that you can use that are going to make it star-like, right? Or really the disk with a slit. But it's this is one possibility, right? But this function over here is holomorphic there. This C1 is a closed C1 path, a cycle, right? So therefore, its integral is 0, right? Oops, sorry. I already went to the next to the thing that I wanted, right? So the integral around here is 0, right? And similarly, for the same exact reason, with just a different domain, you get that the integral around C2 is 0, right? So the integral around C1 plus the integral around C2 is 0, right? Well, what is that? As chains, the integral around C1 plus the integral around C2 is supposed to be equal to integral around gamma minus the integral around alpha. This thing is 0. What does that mean? That means that the integral around alpha equals the integral around gamma, right? These guys are equal, right? So that's basically what we proved, right? Now that's useful because we've done essentially one of these computations. We've done computation like the thing on the right over here. We've done before. It's really easy because now alpha is a circle that's centered at z. That's going to make this, I can compute this thing explicitly very easy. Whereas over here on this side, it's not quite so easy because this gamma is not centered at z. Alpha is centered at z, right? So let's parameterize alpha, right? I mean z plus something that goes around. Let's use t as a parameter, right? Just a standard parameterization of a boundary of a disk, and let's write let's compute this integral over here, right? So I just write down the definition of a path integral, right, using this parameterization, right? So you have over here, right, the zeta, that's this bit, right? That's the parameterization. Over here, I have that's alpha prime, right? That's why I'm getting this I out here, right? This is coming down when I differentiate, right? And the z, of course, disappears. It's a constant, right? And again, this is f of zeta, right? And I'm going from 0 to 2 pi, right? And I have this 1 over 2 pi I in there, right? All right. Well, cancel things out that need canceling out. Of course, the z cancels out the z. That's the reason, I'm saying this is easy to compute because it's centered at z, right? So this thing cancels out nicely. Otherwise, things would be ugly. So therefore, the SEIT, right, cancels the SEIT out here. There's still an I left that cancels out this I, right? And so what I end up is this guy over here, right? Now that looks a lot nicer, right? Now, if we do this, right? So notice that this integral, right? This quantity over here, it doesn't really care what s is, right? It's it's independent of s. It's for every s, it's that quantity, and that equals this quantity, which a priori does depend on s, right? Because alpha depends on s, right? I mean, it's an integral around a different, around a different different circle, right? Now, for small enough s, right, we've shown that these two guys are equal. That means I can take a limit, right? I mean, it's just limit of constants, right? I mean, it's clear that I can take a limit here on the left-hand side. Therefore, I can take a limit on the right-hand side. It's also constant, right? So we can take a limit, and well, the limit of here, well, that's that's what it is, and then that equals the limit of this quantity, because that's equal, and it's actually a limit of a constant, right? So I mean, it's clearly equal to, right, this thing, right? However, if I write down what I wrote out over here, that this quantity is equal to this quantity, right? Then it equals this. I mean, it's still limit of a constant. We're just trying to figure out what that constant is, right? But now, what is this, right? Sorry. This, this is an integral from 0 to 2 pi divided by 1 over 2 pi. So this is the average of the value of this, so the average value of f on a little circle of radius s, right? So again, just like before in the last section, as s goes to 0, right, this thing goes uniformly to just f of z, right? Again, you could write down sort of a more explicit estimate here, but well, this thing just goes to f of z, right? So the limit has to be f of z, right? I mean, it was a limit of a constant, right? I mean, the whole point is that we need to figure out what that constant is, right? And it's easy to figure out what it is in the limit, right? Well, since it was in the limit, it's actually any one of these is equal to f of z, right? But we had to figure it out by taking the limit. Maybe a little bit weird, but yeah, that's what we do. Right. So that's Cauchy steering for a disk. So we'll see some applications of it in the next lecture. Okay, so let me stop this. Oops.